previous one. Yeah, perfect. Thank you. All right. So my talk is Python, Rust, and regexes. Yeah. Yeah. Okay. So who am I? My name is Nisanthan. I'm a senior engineer at Sentry. The most recent trip I've done is hiking through the Amazon rainforest. So, yeah. So today I want to talk about a feature we have in Sentry and how I went about trying to scale that feature. Along the way, that we're going to talk about Python, Rust, and regexes. So what is Sentry? Sentry is an error and performance monitoring tool that gives engineers comprehensive visibility into their code so they can see the issues in matter of real time, solve them faster with actionable details, and learn about the historical trends to optimize code health over time. Key features were open source, and were primarily Django and React, with a couple of random microservices here and there. So you've just built the next big app, like a social media app, which I'm assuming is now Be Real. I don't know. And you've instrumented it with Sentry's SDK. You've launched it, got your first users, and now you got your first bug in production. Now what? We want to figure out who is the person that can resolve this issue and assign it to them. There we go. So this is kind of how it looks like in the UI if you've never used Sentry before. So the tools that we have to accomplish this. So pre-COVID, we had something called ownership rules. It's essentially allows you to create rules on the Stacktrace, URLs, or event tags. This was the original method that we provided for issue ownership. During COVID, the industry kind of coalesced around code owners, which is set by GitHub, GitLab. I don't know if any of you guys have used it. But if not, it essentially allows you to write git ignore style paths and assign it to like GitHub teams and individuals on GitHub. And so it turned out most companies wanted to maintain one set of rules, and that's going to be code owners. So we kind of built tooling around that. Oh, okay. So import their code owners file. It's just pretty easy, right? But not really. Source code file paths do not equal Stacktrace paths. The lines in your code owner's file that represents the source code file paths are error events capture a Stacktrace whose file paths are not going to be one-to-one. Your CI, like continuous integration, continuous deployment pipeline, will transform, bundle, and minify your code. We need a way to reverse engineer that process, which is why we have something called code mappings. We have an automatic process to derive these mappings, and that allows us to essentially get an equivalent Stacktrace file path from your source code file paths. The problem is that there could be like n number of code mappings. For example, like you have a microservice architecture in a monorepo, so you'll have an explosion of these mappings. All right, so enough background. This is kind of like the simplified code that runs this feature. You're going to have like a list of code owners, like these transformed code owners. And for each rule in that code owner's file, we're going to have to go through each file path in the Stacktrace and generate a regex for that path, like that git ignore style path, and do like a regex search for a match, right? Does this scale? Uh, Probably not. It's big O n squared time complexity. We calculate on every event. Code owners can get up to 3 megabytes. We currently have limited to 100,000 characters, and we're trying to get it up to 3 megabytes. So that's the real problem here. So ideas on solving that. Uh, One idea was to use Rust regex engine. Um, it's well known for being very quick. And the second option was to use a trie or tree. We looked it up. It's actually called trees. For those of you who don't know what it is, it's essentially a tree data structure where lookups are O of m, where m is the string's length. The trade-off here is space complexity. If I remember correctly, it's O m of n. And so, for example, if you have like code owners paths like this, right? The tree structure we've been generated like that. The problem is that for paths where the glob pattern is in the middle of the path, you still require a regex engine for these types of cases. So my plan was to just start with idea number one, which is to optimize to rewrite it using the Rust regex engine. So rewrites, always fun. So basic idea was to use to call the Rust engine through an FFI. So Rust gets transformed into like a C application binary interface, and that's used that's called by our C Python code. So I just kind of grabbed some simplified screenshots of our code. And so the Rust code essentially translates the code owner's pattern into like a regex and then runs isMatch, right? Pretty straightforward. The top level macros. So the first one is no mangle. That's a macro that prevents the compiler from mangling the symbols. This is because C does not understand the mangling. The second one is our own relay FFI catch and wind macro, which captures errors and panics in a thread local on unsafe functions. And then this is our Python library that calls the Rust functions. I don't know if you can see, but like Rust call, it's just a utility function that handles calling our Rust code. So now we just have to cut a new library release, and we can use this method in Sentry. So we rewrote it in Rust. Now what? Is this an improvement? We got a benchmark. Here comes PyPerf. There's a PR, like a draft PR, that handles, that outlines all of the testing that I did. But I'm just going to run through it really quickly in slides. So the test conditions, we want to replicate the expected max load. So that's going to be like a 3 megabyte code owners file with 5 code mappings, equivalent to like 15 megabytes of stuff. And when I ran it, it's not really much of a difference. Python and the Rust implementation was pretty similar, both CPU time and memory-wise. So I want to run a benchmark test where the implementation diverges, specifically when we start calling the the Rust code versus the Python code. And I could see that the Rust implementation was really slow. Why was it slow? Regex compilation takes a long time, but that didn't really make that much sense because it should be slow for Python as well. So it was time to look at source code. So looking at the Python source code, I don't know how to open up a link on this thing, but essentially, this presentation is a website, but if you click in, you can see that there's a point in the code where we cache the compile regexes. So good artist copy, great artist steal. I'm assuming it works for programmers too. So for my Rust implementation, I used like an LRU cache, which is like a least recently used cache to speed it up. And so time to benchmark it again. Now it's much faster. The times are a little bit slower for Python because I added more of a realistic stack trace, so like more file paths in the stack trace. But it kind of shows how like the cache is much faster, right, after using caching. So it's faster, but we want to test it in prod, because also I got this weird error from PyPerf saying that the benchmarks were unstable, because I wasn't using like an M1 Mac. I was using like the old Intel Macs, so I think that's the problem. So we feature flag it to our Sentry org, and I run the benchmarks. And the mean and median is pretty much the same, but the real difference is in the P99. That shows the difference in speeds. And when I test with the 15 megabytes code owners, you can really see the main differences here. It's faster, but the magnitude wasn't as fast as I was expecting. Python's regex engine is pretty fast already, and it's pretty optimized for speed. So is this good enough? Probably not. Shortcut in engineering, change the system requirements. Do I really need to calculate on every event? Nope. We should debounce events and prevent unnecessary calculations. So it should be good enough with that change in requirements. So monitor and limit it to fallout. And if this isn't enough, we can always implement the trie. But that comes with like its own complexity as well. And it's not really a silver bullet, so we still need to benchmark and test that solution as well. What we could have done better, we should have gathered the current system metrics in the beginning. This was kind of done ad hoc while I was making the Rust implementation. And the second thing was we could have used a profiler to see where the code was slow. Sentry has a profiler now, FYI. But it doesn't work for celery tasks yet. I think that's upcoming. So I've let them know that this was a limitation. Yeah, that's pretty much it. Any questions? Oh. I believe it's 3.10. Yeah. Yeah. So what actually ends up happening is we have a function that converts the code owner's file path into a regex itself, right? So that regex is, yeah, it can do exactly, yeah, yeah. And so I just had to translate that. That was the part of the rewrite, the fun part, where you essentially take the Python code, rewrite it in Rust, but it does the exact same functionality. So yeah. Yeah, Josh, go for it. Memory wasn't really a concern, just because I remember that celery tasks in production run with a lot of memory. So, you know, yeah. Yeah, exactly. Yeah, that was like, that's why I didn't want to do the tree yet, because then I know I have to think about memory. Any other questions? Yep. Perfect.
Thank you.
Thank you.
Thank you, Nisanthan. Okay, that was excellent.